Hello students, hope you are doing well. Welcome to my channel where we nurture and learn mathematics beyond boundaries. In today's video, we are going to cover linear programming problem topic as part of class 12 Applied Maths CBSE curriculum. Now before we get into the details of linear programming problems, let's first understand the weightage of this chapter in your board exams. This chapter carries a weightage of 8 marks in your board exams, wherein you are going to get a question, 5-marker question on this, and then a 2-marker question, and then 1 or 2 MCQs. So it's very important that you understand the concepts clearly, understand all the possible scenarios while you are attempting LPP problems, so that you don't face any issues while attempting your questions in your exam. Now in this video I have captured certain questions from, both from CBSE Handbook and from ML Agarwal, just to make it comprehensive and to give you exposure to all the possible scenarios when you are solving or formulating a linear programming problem. So let's first understand what is a linear programming problem. So it is a problem when we have to determine an optimum value for a given linear function subject to certain constraints in the form of linear inequalities, then we call it a linear programming problem. So what are the components of an LPP? The first is the decision variables, where we have certain quantities represented normally by X and Y, that represent maybe the amount of units produced for any product, or maybe the amount of food that you are taking in for any kind of diet problem. Then there is an objective function that needs to be optimized as per the linear constraints. Optimized means either you might have to find a maximum value or the minimum value of the objective function subject to some linear constraints, and then there are some non-negative implicit constraints also. The objective function could be something like where you need to maximize profit or you need to minimize the cost based on certain explicit constraints as per the production process or the foods that are under consideration. So the objective is always to optimize this objective function subject to certain explicit constraints. Implicit constraints are to be mentioned, even though they are not there for anywhere for the solution, but they need to be mentioned because we are always considering the first quadrant of the graph when we are finding the optimum solution. So there are two ways in which you can solve an LPP. The first is corner point method, and second is ISO profit and ISO cost method. So we do not have ISO profit and ISO cost method in our syllabus for 2025-26. So our focus is going to be on the corner point method to solve an LPP. Now there are 4 different types of LPPs. First is manufacturing problem, where you are manufacturing certain products, maybe nuts and bolts or maybe tables and chairs or anything, and then we need to optimize the cost or optimize the profit that we are making out of those manufacturing things. Then we have diet problems, where need to mix certain foods to meet the dietary requirements of an individual. And then we have transportation and assignment problems also. But again, as per this curriculum for 2025-26, we do not have transportation and assignment problems in our syllabus. So we are going to focus on manufacturing and diet problems. Now how do we formulate a linear programming problem before even solving it? So the first thing is identify the objective function that you need to maximize or minimize. What is to be done with the objective function, maximization or minimization, even that is important. Now what are the dependent variables in the scenario given to you? Represent them using X and Y. Now create inequations for the explicit constraints. If the question has the keyword at most, maximum, then that means the inequality will have less than equal to. And if the question has keywords like at least or minimum, then inequality will have greater than equal to, right? And then you need to specify the implicit constraints also, that is X is greater than equal to 0 and Y is also greater than equal to 0. So one LPP has these 3 main components. The first is the objective function subject to some explicit constraints, and then the implicit constraints, right? Now let's see how to solve an LPP. What are the steps involved? The first step is to plot the graph of the explicit constraints. These are linear inequalities and you need to plot the graph. After you have plotted the graph for all the linear inequalities or all the explicit constraints, you need to identify the feasible region. So when we'll solve questions, you will get a clear picture of how to identify the feasible region. Now once you have the feasible region could be bounded or it could be unbounded also. Bounded means it is bounded by some lines and there are few corner points involved. Unbounded means It is bounded by lines or maybe on maybe 2 or 3 sides, but it is open in one of the sides. So there are few corner points, but still it is unbounded. So there can be more than one solutions in such cases. So we'll solve questions related to bounded regions also, unbounded regions also, so that you understand all the possible comprehensive, all the possible scenarios for any kind of LPP. For the bounded region, you will get the optimized value of the optimal function at one of the corner points. So you might even need to solve certain equations algebraically to find the point of intersection, that is one of the corner points, and then find the value of the objective function at these points. Now for the unbounded region, the extra step that is needed is you need to plot the graph of the objective function also, and then decide whether there is one solution, there are more than one solution, or there is no solution at all. So there are 3 cases for unbounded region. So we'll first start with the questions on the bounded region. So before we get into the solution of an LPP, let's see how do we formulate an LPP. So the first question is, a furniture manufacturer makes 2 products, chairs and tables. So we have chairs and tables, and the processing is done using 2 machines, A and B. So it is A here, B here. A chair requires 2 hours on machine A and 6 hours on machine B, whereas a table requires 5 hours on machine A and no time on machine B. There are 16 hours per day available on machine A. So machine A can be used for maximum 16 hours. After that it is not available. So that means 2 and 5, the limit for machine A, it is available for maximum 16 hours. So that means the usage has to be less than equal to 16 hours. Then machine B is available for how long? 30 hours on machine B. So machine B is available for maximum 30 hours. You cannot use it beyond that. Now profit gained by the manufacturer from a chair and a table is rupees 2 and rupees 10. So it is rupees 2 here. This is the profit, and it is rupees 10. Right? Formulate this problem as an LPP to maximize the total profit. So you need to maximize the total profit. Now here, if we take, you have to write it explicitly. Let the number of chairs. Please write this, what is X, what is Y. Let the number of chairs be X and number of tables be Y. So this is X and this is Y. Now what is the objective function? Objective function is to maximize profit. This word is important. Don't skip whether it is maximize or minimize. Maximizing, and the objective function is 2 times X plus 10 times Y. This becomes the equation for the objective function. What are the explicit constraints? Write this phrase, subject to constraints. So what are the constraints? 2x plus 5y should be less than 16, and then 6x should be less than equal to 30, and the implicit constraints are x should be greater than equal to 0 and y should be greater than equal to 0. So this is your formulated linear programming problem for the scenario given to you in this question. Right? Easy? Wonderful. So let's move to the second question. A diet is to contain at least 80 units of vitamin A and 100 units of minerals. So 80 units of vitamin A and 100 units of minerals is what is needed. 2 foods F1 and F2 are available. So where is F1? This is F1 and this is F2. You have 2 foods. Food F1 costs rupees 4 per kg. Now you are given the cost of the foods. It is rupees 4 per kg. And the cost for F2 is rupees 5 per kg. 1 kg of F1 contains 3 units of vitamin A. So it is 3 units of vitamin A and 4 units of minerals in the food F1. 1 kg of food F2 contains 6 units of vitamin A and 3 units of minerals. So it is the composition of F2. We wish to find the minimum cost for the diet that contains mixture of these 2 foods and also meets the minimum nutritional requirements. Formulate this as an LPP. Now you need to minimize the cost. So the objective function is, you need to write minimize. This word is again important. Minimize Z equals, suppose the quantity of food F1 is X and quantity of food F2 is Y. Write what is X and Y. Write it explicitly and then only mention the objective function. So it becomes 4 times X plus 5 times Y. subject to constraints. Now what are the constraints? Subject to constraints 3x plus 6y. Now this is the minimum requirement that you need at least, the question says at least. That means the amount of vitamin A can be more than 80, but it should be at least. So it has to be greater than equal to. It has to be greater than equal to. At least vitamin A and minerals. So 3x plus 6y is going to be greater than equal to 80 and 4x plus 3y greater than equal to 100. And the implicit constraints, very important to be mentioned very clearly. Put it in a box if okay, so that the entire LPP is clearly visible, all the components, the objective function, whether you need to maximize or minimize, the explicit constraints and the implicit constraints. Everything has to be there when you are formulating an LPP. Now let's look at how to solve an LPP once you have formulated it. So now this is an LPP where you need to maximize z equals x plus y subject to some constraints. The implicit constraints xy greater than equal to 0. The first constraint is x minus y less than equal to minus 1 and x is greater than y. So the first step while we are solving any kind of linear programming problem is to plot the graph of the constraints that are given to you. So how do we plot a graph? Make a xy table. So we are interested only where this graph is going to intersect the x and y axis. Even though you can take any point and plot the graph, but preferably use when x is y, what is the value of y, when x is 0, what is the value of y, or when y is 0, what is the value of x. So when x is 0 here, y is 1, and when y is 0, x is minus 1. So let's plot this. X is 0, then y is 1. This is one of the points, and when y is 0, x is minus 1. It can have a negative value even though we are interested in the first quadrant, but for drawing the graph of the inequality, it may go into the negative quadrant, so it is perfectly okay. So now how do we draw this? The graph of this inequality is going to be like this, right? Second inequality, x is greater than y. Make the xy table. If x is 0, y is 0. So both x and y 0 are already covered. So you take some other value. For example, if x is 2, what is the value of y? Y is also 2. So that means it is again going to be a straight line passing through the origin. So this is the second inequality where we have a straight line passing through the origin, right? So these are the two inequalities. Now where is the feasible region we need to find out. For the first inequality, mark the graph, also the inequality also. Second one, label it as 2, mark it as 2, because it will save your time when you are finding the feasible region or solving the LPP. Now for the first inequality, after you have drawn these lines, you need to find the feasible region. How do we do that? Look at any point, because this line is dividing this plane into two halves. So take any point and try to figure out if this inequality is fulfilled or not using that point. So this will help you decide the feasible region. For example, the first inequality is here. So if I take a point 0, 0 at origin, 0, x is 0, y is 0. Is 0 less than equal to minus 1? No. So that means the feasible region is on this side of the inequality graph. So use these arrows, they will always help you when you are solving these problems. The second equation, x is greater than y. Now if I put any point, for example this point, x is 2, y is 0. X is 2, y is 0. Is 2 greater than 0? X is 2 and y is 0. So where will be the feasible region? X is 2, 2 is greater than 0. Yes, definitely it is there. So that means the feasible region is on the side where you had the point 2, 0. So this is the feasible region for inequality number 2. Now as you can see, there is no common feasible region between both the explicit constraints. So that means z cannot be maximized here. Z cannot be maximized and there is no solution for this LPP. Right? So the feasible region has to be common between the feasible region of both the inequalities. If there is no feasible region that is common between both of them, then there is no solution as such, right? So now we'll look at two questions on bounded feasible region, where you have a simple bounded feasible region and you are easily able to figure out what is the maximum minimum value at one of the corner points. And the second scenario is going to be where you have a bounded region but there are more than one solutions. So let's have a look at it. Minimize this objective function subject to certain constraints. So we always start with the constraints, x plus 2y greater than equal to 10. Let's plot the graph of this. So before the graph make the table. When x is 0, y is going to be 5. When y is 0, x is 10. The next constraint is 3x plus 4y less than equal to 24. Make the table for this also. What is x? When x is 0, y is 6, and when y is 0, x is 8. So now let's draw the graph for this inequality and see where is the solution or the feasible region. So the values are very small. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So please mark all the axis and the origin, mark all the parts of the graph very nicely. Now x plus 2y greater than equal to 10, this is the first inequality and this is the second one. X is 0, y is 5, 1, 2, 3, 4, 5. So this is the point, 10 and 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 10 and 0. That means this is the graph of this inequality, right? So this is for number 1. If I put the origin point 0, 0 here, 0 is greater than 10. No, it is not. So that means the feasible region is going to be somewhere on this side, right? Now let's plot the graph for the second inequality. X is 0, y is 6. 1, 2, 3, 4, 5 and 6. So this is the point, and 0 and 8. So this is the point. So where is the feasible region for this second line? So this is the second inequality. If I put x and y as 0, 0, it is less than 24. Yes, it is. So the arrows go downwards. Now what is the common feasible region between both of them? This is the common area that is there for both these inequalities, right? So this becomes the common feasible region. Now if I look at the corner points, I know the coordinates of two of these corner points. It is 0, 5 and this one is 0, 6. But for finding the third corner point, I need to solve both the inequalities algebraically. So what do I do? X plus 2y equals 10 and this is 3x plus 4y equals 24. If I multiply the first inequality by 2, I get 2x plus 4y equals 20. And then solving this gives me a value of x as 4. If I put x as 4, 10 minus 4 is 6 and half of 6 is 3. So that means y is 3. So that means this point of intersection is 4, 3. So I have three corner points A, B and C, right? Now once I have the graph, I have the feasible region, I have all the corner points, I need to make a table where I find the value of the optimized function at each of these corner points. So the first corner point is 0, 6, next it is 4, 3, next it is 0, 5. Okay, so the objective function is 200x plus 500y. Now find the value of z at all these corner points. So when it is 0, 6, the objective function will be 3000. When it is 4 and 3, 4 to the 8 and 5 3 is 15 and it becomes 2300 and 5 5 is 25, so it is 2500. The objective was to minimize the function. So the minimized value or the lowest value is this. So that means this is the minimum value of z, 23, at x equals 4 and y equals 3. So this is your solution, right? So it is very easy when you have a bounded region and there are some corner points and you get the minimum or maximum value at one of these points. Now let's look at another example where you have a bounded region but there is no one fixed solution. Let's see. So the question says minimize and maximize z equals 2 plus x plus 2y subject to some constraints. So we'll again start with the explicit constraints. X plus 2y greater than equal to 100. Make the table for xy, and the second constraint is 2x plus y less than equal to 200. Again make the table for xy first. When x is 0, y is 50. When y is 0, x is 100. When x is 0, y is 200, and when y is 0, x is 100. So let's plot the graph for both the inequalities. Label both the axes, mark the arrows, don't make such silly mistakes, you will lose on marks here. So label the graph properly first. Now we have the points 100, 200, 50 and 100. So I can take it as 50, 100, 150, 200, 50, 100, 150, 200. Use a proper scale as per the values that you have. So when x is 0, y is 50, this is one of the points. When x is 100, y is 0, so this is the other point. So let me join them. This is the graph for the first inequality. Label it as 1 here also and here also. Let's look at the feasible region. If I put the origin 0 and 0, is 0 greater than 100? 0 is not greater than 100. That means the feasible region is on the upper side of this line. Next, 2x plus y, when x is 0, it is 50, 100, here this is the point, and when it is 100, y is 0 and this is 100. Okay. So let me draw a line from here to here. Right? So this is the second line. Now we have another constraint also. I think there are 3 constraints given in this question. X plus 2y, 2x plus y less than 200. Okay, we have taken this one also and we have taken this one also. So the third constraint is 2x minus y less than equal to 0. So let's plot this also, x and y. When x is 0, y is 0. So that means let's take some other value other than x and y. When x is 4 to the 8, y is, or maybe let's take x as 50. When x is 50, 50 to the 100, so y is 100. So x 0, 0 and the other points are x is 50. So it is here, then y is 100 here. So one point is 0, 0 and the other is 50 and 100. 50 and 100 somewhere here. So I am just drawing approximate graphs because you will have an exact graph paper, so you will get the exact graph. So don't worry. Right? So this is what we have. The graph looks something like this. Yes? Now where is the feasible region for this 0, 0? If you look at this inequality, 0, 0 and 50, 100, this is inequality number 3. So just label the graph also. This is for 3, this is for 2. Now where is the feasible region? For this we have marked the arrows. For the second inequality, 0, 0 is less than 200. No, it is not. 0 is less than 200. So that means the feasible region is on this side of the second inequality, and the third one, 0, 0 less than equal to 0. Okay, let's take the point 1 and 0. If x is 1, y is 0, so it is 2 minus 1, 0, 2 minus 1 is 1, 1 is less than 0, no. So that means for this the arrows are going to be this side. So it's very important you use these arrows, that will help you identify the common feasible region, right? So now where is the common feasible region? It is this area. So this area is common between all the feasible regions for all the 3 inequalities. Now we need to find the coordinates of, we have one of the coordinates A, B, C and D. There are 4 corner points. We know the coordinates for A and B. Let's find the coordinates for C. C is the point of intersection of 3 and 1. So let's solve 1 and 3 together. So it becomes x plus 2y equals 100. and the third one is 2x minus y equals 0. So this means y is equal to 2x. So x plus, in place of y you put 2x. 2 into 2x is equal to 100. 4 and 1 5. 5x is 100, that means x is 20. When x is 20, what is the value of y? Y is 40. So that means the point of intersection of the first and third line is 20, 40. So this is the point of intersection. Now we need the point of intersection of the second and third line. So these two lines. So it is 2x plus y equals 200, and this is 2x minus y equals 0. So if I add both of them, I get 4x as 200. That means x is 50. When x is 50, y is 100. So at this point, the value of x is 50 and y is 100. So you have the coordinates of all the corner points. Let's label the other points also. What is point B? Point B is 0, 50, and this point is 0, 200. So we have all the corner points. Now we need to minimize as well as maximize the objective function. So here when we have to minimize as well as maximize, let's find the value of the objective function at all these corner points. So z is x plus 2y. So the points are 0 to 100, then B is 0, 50, then C is 20, 40, and then we have D as 50, 100. So what is the value of the objective function at point A? It is 400. At point B, 0 and 50, the objective function will be 100. At point C, 20 and 40, again it is 100. And at point D, it is 250. Now the objective was to maximize as well as minimize. So what is the maximum value here? This is the maximum value. And minimum value, we have more than one minimum value. Now what do we do? How do we write the answer? Where are the minimum values? B and C. So that means this area between B and C, this entire part of this graph, the entire part of this line B and between B and C, all the points on this line are a solution for this objective function. They are going to give you the same minimum value, which is 100. So for maximizing the function, we have the solution. The maximum value of z is 400 at x 0 and y 200. So this part is done. It is very clear. At x, this is the maximizing point. Here we have the maximum value. But where do we have the minimum value? For the minimum value, we have the entire line. So there is no one optimum solution for minimum value. Even though the minimum value of the function is 100. We know the minimum value, but there are infinite points. So you can write it is at B 0, 50. Rather than writing the coordinates of the points, it's always good to specify what is the value of x and y when you are writing the solution. At x is equal to 0, y 50, and it is also at x is equal to 20 and y is equal to 40. So therefore, there is no one optimum solution. So there are more than one solutions to minimize this objective function, right? All the points on this part of the graph BC, they are all the solution for this objective function. They are all going to minimize the objective function. So what if if two corner points give you the same minimum or the maximum value, the entire length of the line segment, all the points on that line segment give you the same minimum or maximum value, and then we have infinite solutions. There is no one optimum solution, right? So now we'll have a look at certain unbounded feasible regions where we have different scenarios. It could be for unbounded regions, we need to go one step further and draw the inequality for the objective function also. Now there could be three scenarios here. One is there is just one optimum solution. Second, there can be infinite solution. And third, it is possible there is no solution. So we'll just have a look at all the three scenarios for an unbounded area. When do we have a solution, when do we have infinite solution, and when we don't have any solution. So the first question is minimize the objective function subject to certain constraints. Again, we start by plotting the graph of this these constraints. So x plus 3y minus 3 greater than equal to 0. Draw the table for x and y. When x is 0, y is 1. When y is 0, x is 3. So let's draw the graph also side by side. So I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So x is 0, then y is 1. This is one point. When x is 3, so this is the other point. That means the graph of the first inequality is here. So I need to label it as 1, mark it as 1. If x and y are 0, minus 3 greater than 0, not true. Minus 3 is not greater than 0. So that means 0, 0 is not the point in the feasible region. So the feasible region is on the upside of this inequality. Now let's look at the second explicit constraint. X plus y minus 2 greater than equal to 0. Make the table of x, y. When x is 0, y is 2. When y is 0, x is 2. X is 0, y is 2. And when y is 0, x is 2. So let's draw the second inequality. So this is the second inequality. Now if x and y are 0, 0, minus 2 is greater than 0, no. So that means again the feasible region is on the upper side of this second inequality. Now where is the feasible region? How do we get the feasible region of this graph now? So here this unbounded area is the feasible region for this problem. Now because this area is unbounded, we need to go one step further. So do we know the corner point coordinates? So this is 0, 2 and this is 0, 3. So we have two corner points, but we don't know the value of this third corner point. So let's solve both the inequalities algebraically and find the point of intersection for both of them. So this becomes 2y equals 3 minus 2 is 1. So that means the value of y is 1 by 2. And if I put y as 1 by 2, x will be 2 minus half, which is x gives 3 by 2. So that means the coordinate of this point of intersection is 3 by 2 and then 1 by 2. So we have 3 points A, B and C. So we have the three corner points, but where is the objective function maximized or minimized? How do we find that? Again, plot the table, make the table for the corner points and the objective function. So the three corner points are 0 and 2, 3 by 2 and 1 by 2, and then we have 0 and 3. The objective function is 3x plus 5y. So what is the value of this objective function at these corner points? Sorry, it is not 3, 0. The coordinates of point C are 0, 3. It is not 0, 3. It is x is 3 and y is 0. So I'll just rectify this. So the corner points of this are 3 and 0. Okay, now what is the value of this objective function at 0, 2? 0, 2 is going to be 5 2s are 10, so it is 10. Now at 3 by 2, x is 3 by 2, 9 by 2 plus 5 by 2. So it is 9 by 2 plus 5 by 2. What is the value of the objective function at x is 3 by 2 and y is 1 by 2? So it becomes 9 by 2 plus 5 into 1 by 2, 9 by 2, 5. It becomes 14 by 2, 14 by 2 becomes 7. Okay. Now what is the value of the objective function at 3, 0? 9 and then 0. So it is 9. Right? So these are the values you got. Now the question was to minimize the objective function. So the objective function was to be minimized and we have the minimum value at b, that is 7. So the minimum value of this function is 7 and the point at which it is minimized is x is 3 by 2 and y is 1 by 2, right? Okay. Now this is your solution. So the minimum value of the objective function is at one point. There is one fixed solution. Now let's look at another objective function where we have the unbounded feasible region, and let's see whether we have just one solution or we have infinite solutions or we have no solution. So let's start with this. So here we have 2x plus y is greater than equal to 3 and the other constraint is x plus 2y is greater than equal to 6. Make the xy table for both the inequalities. When x is 0, y is 3. When y is 0, x is 3 by 2 and this is 1.5. For the second inequality you have when x is 0, y is 3 and when y is 0, x is 6. Now let's plot the graph for both these inequalities. Okay, when x is 0, y is 3. So this is the point. And when y is 0, x is 1.5. So this is the point. So the graph for the first inequality is somewhere like this. The points are x is 0, y is 3 and x is 1.5 and y is 0, right? So this is the first inequality. We have marked it here also. 0, 0 is greater than 3? No. So that means the feasible region is on the right side of this. Let's plot the second one, 0 and 3. 0 and 3. So it is a common point and then 6 and 0. 1, 2, 3, 4, 5, 6, 6 and 0. So that means this is going to go like this. 1, 2, 3, 4, 5, 6. Yes. So this is the graph for the second inequality. 0 and 0. 0 is greater than 6? No, it is less. So that means the other side. So again the feasible region is on the right side. So where is the feasible region? Again you got unbounded feasible region on the right side of both the explicit constraints. Do we have all the corner points? This corner point, yes, it is 0, 3. This is point A. And the second corner point is this B at 6, 0. So we have both the corner points. We don't need to solve them algebraically. We have the corner points. We have the feasible region, common feasible region also now. Now what do we do in such cases? Because we have the common feasible region and we have the corner points also, we find the value of the objective function at both these corner points. Point A is 0, 3 and point B is 6, 0. Objective function is x plus 2y. X is 0, y 3 to the 6, x is 6 ohm. So that means the value of the objective function is the same at both these points. At A also and at B also you got the same value. So it is possible that there are infinite solutions for sure. But are the points on this line actually the solutions, or there is no solution? There is no one solution. So we have always three scenarios: one solution, infinite solution and no solution. So here there is no one solution for sure. There are more than one solution. At least at A and B both these points have the same value. But is this the minimized value, or there are values greater than 6 also possible for this? How do we find that? So now we need to limit this objective function with respect to this minimum value or whatever value we got on the at the 2 points. So because it is to be minimized, so I'll put the less than sign and 6, and now we need to plot the graph of this objective function also. If x is 0, y will be 3. If y is 0, x will be 6. So let's plot the graph. X is 0, y is 3. Again the same point. So that means the objective function, it is 6 and 0. Okay. So that means the objective function is coinciding with this line AB. So what happens when the objective function is coinciding with one of the inequalities? All the points on this line are a solution. So there are 3 scenarios: one solution, infinite solution and no solution. So there is a solution The minimum value is 6. Minimum z is 6, but there is no one optimum solution. So there are more than one optimum solution. X equals 0 and y equals 3 is one of the solution. X equals 6 and y equals 0 is also one of the solutions. And all the points on this line segment AB, they are all the solution for this function. Fine? So there are infinite solutions in this case. Right? Now let's look at the third kind of question on unbounded regions where we don't have any solution. Because we have seen the question on one solution, more than one solution. Now in this question, most likely we are not going to have any solution. Let's look at it. So the explicit constraints are x minus y greater than equal to 0. Let's make the table for this. If x is 0, y is 0. So let's take another value. If x is 4, y is also 4. Okay. Next, the second constraint is 2y is less than equal to x plus 2. So let's make the table for this inequality also. When x is 0, y is 1, and when y is 0, x is minus 2. It's okay if we have a negative value here. So let's plot the graph for both these inequalities. Okay, so it is 0, 0 and 4, 4. So the first graph is going to be a straight line like this. Second, x is 0, y is 1. So this is one of the points. And when y is 0, x is minus 2. Okay, let's draw it and see where it coincides. X is minus 2. So it is going to be something like this, right? So this is the graph for the first inequality and this is for the second one. Now let's look at the feasible region. 0 minus 0, 0, let's not look at 0 here. Let's look at 1 comma 0. X is 1, y is 0. 1 is greater than equal to 0, yes. So that means the feasible region is going to be downside of the first inequality, right? Now let's look at the second inequality. We have 0, 0. If you put 0 and 0, 0 is less than 2. Yes, it is less than 2. So that means again it is going downside for the second inequality also. So where is the feasible region? The common feasible region is this area. Again it is unbounded. And what are the corner points? The first corner point is 0, 0. This is the first corner point. For the second corner point, we need to find the point of intersection of both these lines. So let's solve them. The first inequality gives us x equals to y. And if I put x as y here, 2y equals x plus 2. So in place of y, I can put x, 2x minus x equals 2. That means x is 1 and y is also 1. Okay, so let's just write the point of intersection of both these inequalities, right? Now let's look at the corner points and the values of the value of the objective function at all these corner points. So we have two corner points here, 0 and 0 and 1 and 1. Objective function is x plus 2y, so it is 0 here and it is going to 2 plus 1, 3. Okay, there is a mistake here. The value of x and y, it is going to be 2. X is equal to 2 and then if x is 2, y is also 2. So that means this intersecting point is 2, 2, not 1, 1. So this corner point, I'll change it here. So the value of the objective function here is not 6. 2 2s are 4, 4 plus 2 is 6. It is 6. So the value of the objective function at 2, 2 is 6 and at 0, 0 it is 0. So this is the minimum value, this is the maximum value, what we see from the corner points and the objective function. Now, but again, how do we know whether there is one solution, no solution, or infinite solutions? So for this, we need to plot the graph of the objective function also. So the question was, to maximize. So we need to maximize, that means when we write the objective function x plus 2y, so that means now plot the graph for x plus 2y greater than 6. So maximizing means greater than here. So let's draw the table x and y. What is x here? If x is 0, y is 3. If y is 0, x is 6. Okay, so let's plot it. Now the objective function has to be, you need to draw a dotted line for this. X is 0, y is 3. So this is 1 point, 1, 2, 3, 4, 5, 6. It is 6 somewhere here. So that means the graph of the objective function will be something like this. So it is passing through the feasible region. It is entirely into the feasible region if you see. The objective function is coinciding with the feasible region. So in cases where you have unbounded region and the objective function is coinciding with the feasible region, there is no solution. There is no maximum value that you can find for the objective function. You need to maximize here in this case now, but there is no maximum value. This was the largest value as per what you see. As per the corner points and z table, this is the maximum value. But because the graph of the objective function is entirely into the feasible region, then this means this is not the maximum value. There are values greater than this in the feasible region. So this is the common feasible region. X plus 2y greater than 6, 0 less than 6. So that means this is the final feasible region along with the objective function. So that means all the points in this feasible region. For example, if I have 7 and 1, x is 7 and y is 1. X is 7 and y is 1. 7 plus 2 is going to give me a value of 9, which is for sure more than 6. So that means all the points in this feasible region are going to give me maximum value for the objective function. So there is no solution. There is no maximum value that you can find out, and there is no solution for this objective linear programming problem. Understood? So this was very important. When the z line is coinciding or getting into the feasible region, there is no solution. Whether it is to be maximized or minimized, no solution at all, right? So now let's look at two word problems, one for the manufacturing scenario and one for the diet problem, where you need to formulate the LPP also and then solve it also. This is the kind of question you will get for 5 marks in your board exam. So the question says a manufacturing firm produces gold rings and chains. So we need to formulate the problem also and we need to solve it also after this. So rings and chains, the combined number of rings and chains manufactured per day is at most 24. So let this be x, let this be y. So that means x plus y is at most 24. So that means less than 24 is the production quantity. It takes 1 hour to make a ring and half an hour for a chain. So 1 hour for the ring and half an hour for the chain. The maximum number of hours available per day is 16. It is the maximum available. So it has to be less than equal to 16. That means x plus y by 2 has to be less than equal to 16. If the profit on a ring is rupees 300, so the profit here is, this is profit, this is the number of hours. Profit is rupees 300 and on the chain it is rupees 190. How many of each should be manufactured so as to maximize the profit? So the objective function is to maximize 300x and 190y, right? So this is the objective function. These are the explicit constraints. Do mention the implicit constraints, otherwise you lose a half mark just for not writing the implicit constraints. Now how do we start solving? For both the explicit constraints, let's draw the xy table and plot them on the graph. So when x is 0, y is 24. When y is 0, x is 24. When x is 0, y is 32. And when y is 0, x is 16. So all these are multiples of 4. So we need to choose an appropriate scale also when we are plotting the graph. Okay, so let's take the scale as 4, 8, 12, 16, 20, 24 and so on. Y-axis also 4, 8, 12, 16, 20, 24 and so on. Let's mark the origin also. Now let's plot it 0 to 24. So it is the first point here and 24, this is the point here. So that means the graph for first inequality is something like this. So this is for the first inequality, and 0 plus 0 less than equal to 24, 0 is less than 24, yes. So that means the feasible region is downside for this inequality. Second is 0 and 32. Okay, so we need to extend the graph little bit. After 24 we have 28 and then 32. So it is here x is 0, y is 32 and then x is 16 and 0. So this is here. So if I draw the graph for the second inequality, it will be something like this. And where is the feasible region? 0, 0 is less than 16, yes. So downwards, it is downwards for this graph also. So that means the feasible region is this one. So this is a bounded feasible region. This was inequality 2, this was inequality 1. And we have, do we have all the corner points? Yes, for the first one we have the first corner point is A, 0, 24. This is 0, 0, we don't really need this. This is 16, 0, and then we need to find the point of intersection of both the inequalities. So if I try to solve both of them, x and its y minus y by 2 equals 24 minus 16 is 8. 1 minus half is half, so that means y comes out to be 16. If y is 16, what is x? X will be 24 minus 16, that is 8. So that means the point of intersection is 8, 16. So we have the corner points 1, 2 and this is the corner point C. So we have all the corner points and it is a bounded feasible region, so it is very easy to solve. So make a table, corner points and the maximizing function. So the corner points are 0 and 24, 8, 16 and then it is 16, 0. Objective function is 300x plus 190y. X is 0, 190 into 24. So it is going to be 4560 here. 8 and 16, 8 3s are 24 and 16 into 19, 8 and 16. So it is going to be 5440 and then we have 16, 16 3s are 48. So y is 0, so it is 4800. So the objective was to maximize. Maximize means the maximum value here is this. So that means the the question was how many of each should be manufactured to maximize the profit. So that means now the maximum profit is rupees 5,440 when x is 8 and y is 16. So you don't have to write x and y here because we have products. So when 8 rings and 16 chains are produced. So this should be your final answer. You have to write everything. The maximum value of the profit is 5,440 when 8 rings and 16 chains are produced. Clear? So write it explicitly as an answer statement, right? So let's move to the next question. The last question here, where we have a diet problem. Reshma wishes to mix two types of foods, P and Q. So we have two types of foods here. So let's write first what is given in the question. So it is P and Q, what is given to you. In such a way that the vitamin content of the mixture has at least 8 units of vitamin A. So it needs to have at least 8 units, more than 8 units of vitamin A and 11 units of vitamin B. So vitamin B has to be at least 11. Food P costs, now this is the cost of food P, which is rupees 60 per kg, and the cost of food Q is rupees 80 per kg. Food P contains 3 units of vitamin A, 3 units of vitamin A and 5 units of vitamin B, while food Q contains 4 units of vitamin A and 2 units of vitamin B. Determine the minimum cost. So you need to minimize this. So how do you formulate the LPP now? Minimize Z equals, let the amount of food P be X kg and Y for food Q. So it is going to be minimize 60X plus 80Y subject to constraints. Now what are the constraints? The first constraint is 3x plus 4y greater than equal to 8. Next is 5x plus 2y greater than equal to 11. Mention the explicit constraints, x and y both are greater than equal to 0. Now let's start to solve this LPP with the explicit constraints. 3x plus 4y greater than equal to 8. Make the table and plot this on the graph. So if x is 0, y is 2. If y is 0, x is 8 by 3, which is 2.67, right? Second inequality is 5x plus 2y greater than equal to 11. Let's make the xy table for this also. When x is 0, y is 11 by 2, which comes out to be 5.5. And when y is 0, x is 11 by 5. So it is 5 2s are 10 and then 2.2, right? Great. So we have the table for both these values. Let's plot the graph. Okay. So the values are very small, so let's take care of the scale of the graph. So it is going to be 1 here, 2 here, 3 here, here also we have 1 here and maybe 2 here and 3 here. So the scale is very important when you are plotting these lines. When x is 0, y is 2, so 1 point is here. When x is 2.67, so somewhere here, y is 0. So the first inequality, graph for the first inequality is something like this. So this is the first one. Now the second one, when x is 0, it is 5.5, so it is going to go up, little up. So let's adjust the scale or draw the inequality as it is 0 and 2.2. It is 2.2 and 0, so it is going to be somewhere here. One of the points is here and the other point is way up. So we can just draw it something like this. So it will coincide here, somewhere here with the y-axis where we have. Okay, so let's look at the feasible region. 0, 0 greater than 8, no. So that means for the first inequality, feasible region is upside. For the second one, 0, 0 greater than 11, no. So that means this is also upside. So this is an unbounded feasible region problem, diet problem, where the feasible region is unbounded. But what are the corner points? Do we know all the corner points? This corner point, yes, we know. The corner point for this is, we can write in fraction also. It is 8 by 3 comma 0. And the topmost corner point is, it is, I am writing it here, 11 by 2 comma 0 comma 11 by 2. So this is point this, and we need to find the point of intersection. So let's solve them. 3x plus 4y equals 8 and this is 5x plus 2y equals 11. So let's multiply this equation by 2. It becomes 10x plus 4y equals 22, minus minus minus, and then we have minus 7x and minus 14. So that means the value of x comes out to be, x is 2, and then what will be the value of y? X is 2, 3 to the 6, 8 minus 6 is 2, y is going to be half. So this point of intersection is 2 comma half, right? So we have all the corner points. Let's write all the corner points and find the value of the objective function at each of these corner points. So the first corner point is 8 by 3 and 0. The next one is 2 and half, and the upper one was 11 by 2 and 0. Now 8 by 3 and 0, what is the objective function? What is the objective function? (60x plus 80y). So let's find the value of the objective function at each of these corner points. 8 by 3, this is 0, so 8 by 3 into 60, 160. 6 2s are 12, 120 plus half of 80 is 40, so this is also 160. 11 by 2, 30, 30 and 330. So these are the values that you get for the objective function at each of the corner points. Now if you look at this objective function, again you got two same values, 8 by 3, 0 and 2 and half. So that means this part of the graph is the solution. So there is no one optimum solution, there are multiple solutions. The minimum value that you needed was, minimum value is 160, but there is no common point here. Let's look at the objective function also. Now the objective was to minimize this function subject to these constraints. Because it is unbounded, we have found the minimum value, and now we need to plot the objective function also using this minimum value, which was 60x plus 80y, and because it was to be minimized, so write the inequality less than 160. Let's make the table and let's see what happens with the graph of the objective function. When x is 0, y is 20. When y is 0, x is 160 by 60. Okay. Zero, 0 and 6 2s are 12, 13, 14, 15, 16, 46, 2.6, something like this. When x is 0, y is, it was 80, okay, because it is 80 here, so that means this is 2. So when x is 0, y is 2, and when y is 0, x is 160 by 60, and that makes it almost 2.6, right? So let's plot the graph of this objective function now. This is same as 8 by 3 that we have here. So that means the graph of this objective function is now coinciding with one of the inequalities that we have plotted. So it is coinciding with this inequality. So the graph of the objective function is coinciding with the first inequality. That means in this region it is not getting into the feasible region. So that means there is an optimum value 160, but there are infinite solutions in this line segment, on this line segment, the line segment AB. So there are infinite solutions, even though yes, 160 is an optimum value. So it is not the case of no solution, because the Z-line graph is not getting into the feasible region. It is coinciding with one of the explicit constraints, right? So that means the minimized value of Z is 160, but there is no one optimum solution, there are multiple solutions. So there are infinite solutions for this LPP. Right? So hope you understood all these questions, whatever we have covered in today's video. We have covered all the comprehensively, all the scenarios that are possible, but you need to understand the language of the question and frame the explicit constraints properly. That is a challenge when it comes to a 5-marker question, right? So if you like the video and it was helpful, please share it with your friends so that they also benefit out of it. Subscribe to my channel if you have still not subscribed, and do press the bell icon to keep getting notifications for future videos. Thank you for watching. Keep learning, keep growing.